So hey everyone, and thank you for joining. As Sarah said, my name is Keegan, and I'm with ICF. We are the vendor working on behalf of the sponsors of Energize Connecticut to bring this passive house and all electric homes training series to you all. These trainings are at no cost, thanks to the sponsors of Energize Connecticut, and are part of a partnership with Connecticut Passive House and Build Green Connecticut. As we just said, today's training will be recorded and will be available in our online library afterwards. And a reminder, as part of this initiative, we offer a 75% cost reimbursement for individuals that pursue either a FIAS or PHI professional accreditation. This includes the cost of the training and the exam, and we process the reimbursement once you become fully certified. So if you have questions about that process, reach out to us at the email address that you see at the bottom of the screen. Next slide, Gord. And in addition to the no-cost educational training series and professional accreditations, the sponsors of Energize Connecticut also offer robust incentives for builders and developers who choose to go all electric with their residential buildings or pursue passive house certification in multifamily projects with 5 units or more. The passive house incentive design, as seen on the screen here, includes pre-construction incentives for feasibility studies and energy modeling, and post-construction incentives ranging up to $60,000 for full passive house certification. Uh, Next slide. The all-electric incentive is for both single-family and multifamily buildings. It offers two levels of eligibility with specific design and performance requirements associated for each, and has incentive amounts ranging from $1,500 a unit for multifamily up to $10,000 for single-family homes. Our goal is ultimately for everyone involved in the construction of residential buildings in the state of Connecticut to be aware of these incentives. So if you're interested in learning more, please visit the website or contact us at the phone number on the slide. So for today's session, for questions, please use the Zoom Q&A feature to communicate questions, and we can relay them to Gord. We'll save questions for the end at the Q&A session. And a reminder that today's session is approved for AIA continuing ed credits. So with that, I will introduce Gord Cooke. Gord is a engineer, professional engineer with over 25 years of experience in both low and high-rise residential construction. As an educator, consultant, and highly regarded presenter, Gord brings building science insights to life with a practical, field-tested approach, and his expertise spans applied building science, energy-efficient housing initiatives, innovative HVAC, ventilation, and indoor air quality. So with that, Gord, I will turn it over to you.
Thanks, Keegan, and thanks, Sarah. Appreciate the opportunity to be here again. We had a nice session, was that 2 weeks ago, on
Yep, 2 weeks ago.
electrification. I was asked today to speak specifically on enclosures and even more specifically on exterior insulation, thinking about cost-effective ways of getting that done. So I'll talk for about 55 minutes or so, and then we have time for questions. So hopefully folks can stick around. I know we labeled it as an hour, but in my calendar, it's actually showing 90 minutes. So I'm available if people want to ask questions. So thanks for that. I will give a little shameless plug for those who don't know construction instruction. There's the QR code for our free app. You'll find the app is just say it's free. It's got really cool building science bits and pieces to it. Some manufacturers who partner with us on that app, their animations. In fact, the animations you're going to see today that I'm running are all up here on our app as well. And that I would invite you to come to our CI facility if you like these topics. We run a series of classes. They're each 2 days. It's a hands-on experience. Classroom out front, 50 people or so. Then out back, we have 12 different wall sections. We have a little house inside there to the left of the screen with 3 different mechanical systems to get to play with, try, work on, and so on. So just encourage you to come to CI Live in Denver, Colorado. Look on our website. We've just published our 2026 dates for the 2-day training classes. So just encourage you to come to that. In terms of today's agenda, I thought we would start with just a little bit of where codes are taking us with respect to walls, then rethinking perhaps efficient and effective insulation, and specifically working towards continuous insulation, both the opportunities and challenges. And we'll look at some of the strategies for what we've found to be practical application of of continuous insulation. So we'll start there. As I mentioned, wall system performance is where we're starting with. There is the prescriptive tables for the 2021 code, which would be applicable in your area. Thinking climate zones 4 through 6, depending on who's on the call. I'm showing all of the elements, but we're going to focus today on walls, so I won't show much of the others. But if I focused on climate zones, in this case, 3 and up, the real key here is to look at, let's say, climate zone 5. The prescriptive requirements say R30 or 20 plus 5 or 13 plus 10 or 0 plus 20. In all of those cases, CI means continuous insulation. And I always like to point out, in what world does 20 plus 5 equal 30? Well, that's in the thermal dynamics world. That's where we talk about total thermal effectiveness of a wall. But it's showing you that there is this interest in exterior insulation, giving credit for it, if you will. And so that's useful. This is what, if you're doing a performance path on code, this is what you're modeling the house to. Doesn't mean you have to put this on the wall. It means if you don't put this on the wall, you have to find some other way to make up for the difference that you're seeing in terms of energy performance from these prescriptive requirements. So that's where codes are headed. Clearly an encouragement for, not a mandate for continuous insulation, but an encouragement for continuous insulation. And what we want to do today is explore that and say, why is that? What's the value to that, both from an energy perspective, but also from a safe, comfort, durable, healthy building. So that's our challenge today, or at least our opportunity today. And it does come down to the discussion of the common threads of heat, air, and moisture flow. That is, when we think about the physics, one, we have the structure, but past the structure, we need to think about how a wall manages heat flow, airflow, and moisture flow. I will remind you, although continuous insulation sounds like a heat flow element, we need to remind ourselves that moisture is the number one thing that destroys buildings and building materials, and specifically walls. So even when we think about thermal attributes, we need to think about its impact on moisture as well. So we'll chat about those. And we always like to use the words control layers. This was a concept, at least a language, I would say, that Joe Stebrick has been promoting over the last few years, not thinking about barriers on walls, but rather the wall functions and the control layers for that. So we have the exterior finish at the top, the interior finish at the bottom. That's what the homeowner sees. But in terms of what we're trying to accomplish, in addition to the structure, the fundamental structure, we need to think about thermal control, water control, liquid water control, air control, and vape control. And we'll talk about the attributes of continuous insulation in this language, within these 4 parameters. What are we attempting to build, and how well does it control these 4 elements? So keep that in mind. And in terms of what we're going to key on today is the thermal control, both in the cavity and exterior, if you will, continuous insulation. But those are so that's the key functions we'll talk about today. But we will also see how it integrates with the water control, vapor control, air control layer as well. And when our first conversation has to be, when we think about insulation, what is the thermal boundary? What is it that separates outside from inside, the conditioned space, the area that you pay to heat or cool in order to maintain a comfortable temperature? Today, we're talking about walls, but we also need to think about below grade, above grade elements, whether it's a crawl space is conditioned or not, conditioned basement. So in this case, we're thinking about the thermal boundary with respect to above grade walls. We could chat about others on another day, if you will, or again, come to the CI Live facility and we'll walk through all of those elements. And so how do we improve that thermal performance of walls? And one is the proper installation of insulation. Some are going to say, well, it's the proper choice of insulation. Sure, the type of insulation you're going to use, proper installation of it, then optimizing the R value, the thermal resistance of that wall, And then thinking about choosing the right amount of wood to get rid of that insulator that's not as good an insulator, right? The wood itself is not a great insulator. So how can we optimize that? And ultimately, we'll chat about using continuous exterior insulation. And when we start with thermal performance, we should have a clear sense of conduction heat flow, because the type of heat flow through walls is almost entirely conductive heat flow, assuming you build an airtight wall. And in terms of conductive heat flow, it's a pretty simple formula. It's the area of the wall times the temperature difference across the wall on any given day, divided by the R value of that wall. And if you think about 1,000 square foot of an attic, so 1,000 square feet, if it's 70 degrees inside, and 10 degrees outside, that's a temperature difference of 60. And if I insulate the attic to R60, which is more or less code in your climate zone these days, that would be a heat flow of 1,000 BTUs of heat flow through that ceiling. If we contrast that to a wall, 1,000 square feet of wall, same temperature differential, 60 degrees, but a typical 2x6 wall is R20. So we have 3 times the heat flow through the walls than we do through the ceiling. And it's been easy to insulate ceilings, to just keep dumping more pink fluffy stuff or gray fluffy stuff on the ceiling. So that's why we got to R60. It is more difficult, more expensive, if you will, more complicated to increase the R values of walls. But if in fact we doubled the R value of the wall, if we got to R40, we would cut the heat flow in half. And it's just a common thing that we all need to recognize, that when you double insulation levels, you cut heat flow in half. Now, it's still not as low as the ceiling. What if we went to R60? Okay, now we would be on the walls, that would be 1,000 BTUs of heat flow and have the same performance, if you will. And also understand, in most houses, there's more wall area than there is ceiling area. So we have less insulation, as much as the 2/3 less insulation, and we often have double the surface area in walls than we do in attics. So in fact, we should pay more attention to walls than we have in the past. Kind of been there, done that on the ceilings. Let's now pay attention to the walls. The challenge with the walls, though, as we kind of alluded to, part of our walls are insulated and part of our walls, from a structural perspective, made out of wood, and wood only has an R value of roughly R6, so about roughly 1/4 the amount of insulation. 1/4 of your wall made out of wood, and at an insulation value of 1/4. And it turns out that means there's as much heat flow through the studs in many cases as there is through the entire rest of the wall. And this brings up the conversation of effective R value, and all codes are moving towards the concept of effective R values. Even in that prescriptive table I showed you, because of that emphasis on continuous insulation, you'll notice they equated R30 with R20 plus 5, seeing the value of continuous insulation over top of the studs. So it's the effective R value that we're working towards. And it just, in another form or another talk at this, is the conduction heat flow through the wood is 4 times greater than the similar area of wall, or let's say 1.5 inches of wall next to it. You have higher levels of conduction through the stud than you do through the insulation. So we have to work away at that. And because of that, you'll all have a sense. There's 3 ways to improve the effective R value, not the nominal R value, but the effective R value. 1 would be to put in more cavity insulation. 2 would be to get rid of some of that wood, optimized or advanced framing. Or 3, add continuous insulation over top of the entire assembly. 3 ways to improve that R value. So let's start, though, with the conversation. Here's a typical 2x6 wall. It's showing 30% framing percentage. Some would say I'm lower than that. I would challenge all of you, do a stick count. Let's figure out how much wood is inside your walls. but very often in custom houses, it's 30%. The code actually shows it as being 25%. That is, it assumes 25%. But in fact, we see many times it's as high as 30%. And when you look at its effective R value there at the bottom in the middle, what looked to be an R21 wall, that is, you put R21 in the cavity, the effective R value is 1433. Now, that's not bad. I'm not suggesting that's bad. It's just reality. The question is, how do we improve that? And as I mentioned, you could think about getting rid of some of the wood, increasing the cavity insulation, or adding exterior insulation to that. So that's where you want to get to. When we talk about insulation in the cavity, so let's start with insulation in the cavity. We always like to say we're insulation agnostic. I don't care what kind you use. They all have pros and cons. They all manage heat, air, and moisture flow in different ways. There are trade-offs between them, costs and so on. And it's absolutely acceptable to mix and match in a house for finding the highest performance at the most effective cost. That is, I might use a blown in my attic. I might use a bat in the wall or a spray in the wall, and I might use a sheet foam product on the outside, for example. So different types of insulation in the wall in the house is in fact pretty normal. And what we like to show is if you want to talk R value, other than you look at the second line down, the foam, closed cell foam, it has a higher R value in 5.5 to 6.5. Most of the other insulations, open cell foam, the fiberglass, the high density fiberglass cellulose, they're all in roughly the same range. They're all in that 3.5 to 4.5. In other words, the type of insulation is not nearly as important as how well it's installed, and the right application for it. So, and you will know the bottom piece there that most insulations get their R value from trapped air. The only one that doesn't use trapped air is closed cell foam. It's using other inert trapped gases. That's what gives it its higher R value, just a little better in terms of insulation value. But it's all about the air, and therefore that's being trapped, and it's all about how it's installed is really the critical element. There's just highlighting mineral wools versus fiberglass. When you look at them, is what you really want to do is minimize the amount of fibers, maximize the air spaces, but without causing convection loops within the insulation. So as I say, we're pretty agnostic. Fiberglass bats, blown, sprayed, fiberglass is fine, cellulose blown or spray cellulose, mineral wools, all of those are good materials as long as they're installed correctly. Again, they all have attributes. Some are a little better at sound. Some are better at managing fire and noise. So those kinds of attributes. But from a thermal perspective, what we're interested in, how well do they trap air, tiny little air pockets. Similarly, foams, we're big fan of foams, and high density, low density, both have their applications. Different attributes, right? The open cell is vapor permeable. Closed cell is impermeable. So what do I want? What am I trying to achieve in those walls? I'm just, again, reminding you that as building scientists, we're insulation agnostic. Just make sure it's installed correctly. Pick the one that you like. And it's really the installation. And we've all seen it. We can take pictures all the time of poorly installed insulation packed into walls. We know that doesn't work for us. So we just want to make sure we have that continuous, beautifully installed insulation. And energy raters on this call will recognize there's a grading system. This happens to be grade 3 insulation, which is not good. You can see there's gaps and voids on the right-hand side there and missing insulation. Greater than 2%, less than 5%. At 5%, that would be considered grade 4 and you would fail it. The point of this slide is this is a visual inspection, right? You're just standing back after the insulation's been installed and doing a visual inspection. If you think about a 10 by 10 wall, 100 square foot of wall, gaps and voids bigger than 2% of 100 feet would be 2 square feet. When I stand back and look at that wall, do I see any gaps, voids, compressions greater than 2%? You would rate it as grade 3. If you rate it at grade 3 and put that into your energy model, it reduces the energy performance of that insulation by about 15%. And what a shame, right? Because if this is done and then it's drywalled, the next time this is going to get fixed is 50 to 75 years from now when somebody's redoing that, redoing the finishing of a wall. What a shame that would be. And one of the challenges we have in today's world is people think they can see inside these walls with infrared cameras. So if you don't find this and make sure it's installed correctly, and a home inspector or somebody else comes along and uses an infrared camera, they may be making judgments about how well that insulation was installed, and maybe you're taking off drywall to prove that in fact it was installed correctly. So making sure that you want to get to, there's grade 3 sort of in a graphical format or a pictorial format. There's an example of grade 3 in real life: gaps, voids, compressions, not filling the cavity. We don't want that. Oh, and why is that? Because it's convection loops within the insulation. Gaps or voids bigger than 1/2 inch allow convection loops to move through those air pockets, which degrades the value of the insulation. Remember, the insulation quality comes from the trapped air. If I don't have trapped air, if I have air moving in through it, then it lessens the R value, reduces the R value. What we like to do is to get to grade 1. No gaps, no voids, no compressions, no visible sheathing, areas of very minor compressions, less than 1/2 inch. And what's interesting to me is all manufacturers, all leading manufacturers, the Owens Corning, CertainTeed, Knauf, all of the Johns Manville, all of them guarantee that if you take their training, you will be at grade 1. And they've done the surveys that show that if grade 1 doesn't cost any more time, any more challenges than grade 3. It's really quite straightforward for somebody to grade 1, and it doesn't take extra time or extra cost. So we should always be writing into our scopes of work grade 1 insulation. There's again a nice pictorial of it. There's some examples of properly installed, whether it's bats, face bats, mineral wool, blown in, no gaps, no voids, no compressions of greater than 1/2 inch, and just taking the extra care, if you will, not extra time, it doesn't take extra time, but the extra care and understanding and knowledge to make sure that it's properly installed is the important part. And by all means, spray foam. You'll notice there in the left, the open cell spray foam, there are some gaps, right? Not gaps, but some minor differences. And we give spray foam a little bit of a break because at least there's no air movement through the foam itself. So on the left there, if you had to fill that cavity entirely, you'd end up overspraying and have to scarf it off, and there would be a waste of material. So we don't ask spray foam to be full depth cavity in all cases. Certainly no gaps, that is, no visible sheathing, but sometimes we allow a little bit of a give, if you will, for spray foam and still get the value out of it. It does take a skilled operator in order to get it done correctly, but just showing examples of that spray foam. And if we went back to that effective R value, remember we had 30% wall area, we had 14.33, that's with R21. Okay, so what if we tried to put more insulation in the cavity? This is really what I want to get to. Let's take the highest value insulation that we know of, which would be open cell spray foam at 6.5, 7 per inch. And if we did that and filled that cavity, we'd have a cavity insulation of 35. And notice though that the performance of the wall, the effective R value only went from 14.33 to 16.53. In other words, we got an extra R2 out of what we paid for was R21 to 35. That was an extra R14. But in terms of effective R value, we only got an extra R2. And what you're starting to see here is the diminishing returns of cavity insulation. I'm not saying that don't put in spray foam. Spray foam's wonderful. In terms of air tightness, in terms of its structural integrity, noise control, moisture control, great choice. But in terms of its thermal performance, you might say, is there a better way? Should we be doing something else rather than using that spray foam in the cavity? And if we want to get to higher effective R values. So you're seeing here the limitations, if you will, of cavity insulation. I'll even go so far as to say we have some would say, well, let's do double wall. We'll do two by four walls and get up to 2 by 8, or put in 2 by 8s overall. And you'll see here it's still only getting to 18.91. You've gone to extra insulation, but you don't get a really good effect of R values, only an extra R4, if you will, for a whole lot extra thickness and a lot of extra material, and you're not getting great performance. So the limitations of doing insulation in the cavity, because we haven't impacted the wood. That's what we want to get to. So let's talk about then, let's optimize. Let's get rid of some of that wood. Let's just put in the right amount of wood. And we always like to show the ridiculous examples. These are site pictures that some of you may have seen. And this is just framers who love to use wood. And I'm not sure why, but maybe the windows were missized, all of those sill plates underneath. It's just interesting, right? To see all of that wood. None of these are structural. And we would say, should we use wood more wisely? Could we use less wood to optimize the insulation performance? So just a few examples quickly through of wood used to excess, if you will. Hopefully everybody's having a little chuckle. What is nice is the same folks that sell you the wood down at the bottom left there, courtesy of the APA, American Panel Association. They have a wonderful guide that's, you could hand to an engineer or use for your designer or for your framers, and they show you the 5 or 6 strategies to optimize the use of the product they sell. That is, rather than 3 stud corners, 2 stud corners, ladder framing and intersecting walls, wider stud spacings, properly sized headers, single top plates. And what they will show you, and if you do the math, if you do even 3 of those 5 elements, then you can dramatically improve. Dramatic's an interesting word. You can significantly improve the performance, the effective R value of the wall without compromising the structure. I want to say that again, without compromising the structure. In some applications, tall walls, for example, some seismic areas, you might need more wood. But APA, the guide, shows you advanced framing techniques for every climate zone, for every condition. They'll show you what's possible, so we could use and optimize less wood. If you're doing renovation, of course, this doesn't help you much. A remodel of a house, you're typically not taking out pieces of wood, but in new construction, you could think about optimizing that performance. And simple examples of wall intersections rather than multiple studs in that location. This does create some challenges with respect to insulation. So maybe a blown-in insulation is easier to use in these locations. Or what about, rather than a 3 stud corner there in the middle picture, what about a 2 stud corner there over in the right? And you might say, does that get me my cladding attachment? Sure. So you are going to have to imagine and manage the cladding attachments, the cabinet attachments inside, and so on. But it is possible to do advanced framing. And when you do advanced framing, if I can get from 30% down to 25%, which is first level of optimized phrasing, 2 out of those 5 elements, 2 out of the 5. Remember, ladder framing, 2 stud corners, wider stud spacings, properly sized headers, single top plates. If you do 2 out of those, you're deemed to be at 25%. And notice the R value went from 1433. Do you remember that number? 1433 to 1526. And you're going to go, that's one R value. Like, that's not a lot. Yes, but R1 over R14 is roughly a 7% improvement, 6 to 7% improvement. Oh, that's interesting. I lower my cost of wood and I improve performance by 6 to 7%. That's pretty interesting. If you do 3 of those elements, 4 of those elements, 4 out of the 5, you're deemed to be at 20%. And notice now you're at 16.35, which is basically the same as using high density spray foam in that wall cavity. By doing advanced framing, I improved the performance of wall by R2 over R14, so roughly a 15% improvement at lower cost. And then you'd say, oh, maybe that helps me pay for the spray foam. And now when I put the spray foam in the wall, it actually gets you better performance overall. So just imagining the different metrics and mechanisms to get you that better performance. And there are folks trying other alternatives. Could we use this is called T-stud. I don't know if anybody's seen it, but basically a truss, right, that we're using as that stud. We see opportunities in these areas. You're seeing folks looking at ways of doing this. This, of course, has some other implications. I would need to use a spray foam or a spray insulation in order to take advantage of this, and probably spray foam to take advantage of it. It has some considerations with respect to how do I cut it? How do I, how do I trim around windows? So typically you're still using dimensional lumber around windows and other penetrations, but there are opportunities to find ways of reducing the thermal bridging through the wood itself. We hear all the time about what about staggered stud? Sure, except there's still a lot of wood in that wall. Staggered stud, you still have to maintain your spacing, 16-inch or 24-inch on center. So you basically end up with more wood in the wall. So even though it's staggered, you're still seeing not the full value of that. So these are all opportunities, I would say. By all means, consider these advanced framing and different technologies, but we're seeing the limitations is really the point. We're seeing the limitations of trying to put insulation in cavities in terms of the effect of R value. And if we really want to get to higher levels of performance, like in a passive house situation, for example, R35, 25 to 35 is probably the range. It may even need to be higher. Could I do it with continuous insulation rather than thicker and thicker walls? Could I find a way to improve the performance by using continuous insulation? And lots of examples of that, right? Lots of materials. There's mineral wools, there's expanded extruded foams. Sarah was just telling me that is it Timber HP? If I've got that name right.
Yes,
That
that's right.
yes,
Based in Maine. Yep.
based in Maine, just coming out with just got approval for a wood-based sheathing product, an insulated sheathing product. So lots of choices, lots of materials out there, and we'll highlight those. You might also be asking, well, what about insulated concrete forms or SIP panels? Sure, we can chat about those as well. But I wanted to talk about continuous insulation for the next little bit. And I wanted to show you a 2x4 wall, 30% framing, with R5 on the outside. Look at that wall. Isn't that interesting? You remember our base number, 1433? So we actually could go back to 2x4 with 1 inch of insulation, R5 in this case, inch and a quarter, depending on the medium you're using, and you actually get better performance out of that wall. This is a tremendous opportunity. People think about cost, or you think about smaller houses, zero lot lines, where if I put 2x6 or 2x8 and 2x6 with an inch or 2 inches of foam, my wall actually got thicker. Here's a case where you can make the wall thinner and actually get better performance. So little examples. Here's 2x6 with R5, and now we're at 1933. And of course, I'm going to say combine this with continuous insulation on the outside. Sorry, combine this with advanced framing and get even better performance. Do it with higher performance insulation in the cavity to optimize overall. But I'm showing here incrementally the value of insulated sheathing. And that R5 gives you true value to the outside of that wall. Very, very powerful. And when we're thinking about effective R value, this continuous insulation shows you a really good opportunity, if you will. Now, we often get asked, wait a minute, you're putting insulation on the outside. What does that do to the dew point? And if you were using a foam-based insulation that's presumably impermeable, what does that do to condensation potentials inside of walls? Okay, so here's an animation and understanding that if we have warm, moist air there on the right, moving into a wall cavity, if it hits a surface that's below its dew point, it's going to condense. So if we have air movement through our walls, and if it's cold outside, and I'm just showing a typical January day, for example, in a climate zone 5, temperature outside 20 degrees Fahrenheit. If we have warm, moist air getting into a cavity behind that insulation, we are going to get condensation. So how do we manage that? What do we do to get rid of that? Well, one, never let warm, moist air get in the wall cavity in the first place. So make sure your walls are really, really airtight. Or two, warm up the first condensing surface. That is, if we put an insulated sheathing to the outside and we put enough, in this case showing R10, the temperature of the first condensing surface of the sheathing is now warm enough that I get no condensation potential inside the wall. So one, make it airtight, and two, use insulated sheathing. If you don't want to use an insulated sheathing, and let's say you're doing a thicker wall, like a double wall, a truss wall, something like that, and the thicker and thicker you go, the colder and colder the surface gets on the outside, which means the tighter and tighter you want to make the wall. So I can do this one of two ways: incredibly tight wall or insulated sheathing. Better yet, of course, would be to do both, belt and suspenders. We always want our buildings to be airtight anyway. And then we could say we're going to use an insulated sheathing and warming up that first condensing surface. So indeed, I just want to make the point, continuous insulation on the outside, regardless of the material you use, makes your walls less prone to interstitial inside condensation. So insulated sheathing helps thermally, but it also helps with the durability and sustainability of your buildings. Simultaneously, insulated sheathing makes your houses more efficient, but also makes them healthier from a moisture management perspective. Less chance of condensation wall, regardless of the type of insulation you use on the outside. This is just showing it in a graphical format, the potential for condensation inside of a wall. This is very easy for you to duplicate. We're using, if you look in the middle there, mean daily temperature. That is the outside temperature. That's the dark blue line. Imagine on a January day, roughly 30 degrees Fahrenheit. Is that a typical day? Notice we're not using the coldest day ever. We don't necessarily need to worry about the coldest day. We're worried about condensation over the long term. But notice if the inside air is 70 degrees Fahrenheit and 30% RH, its dew point is roughly 37 degrees. And what we're showing here is for a good part of the winter, most of the winter, there's a potential for condensation inside that wall. And there's 4 ways to fix that. One, don't insulate walls. That's the way they used to do it, right? Old walls didn't have condensation in them because they weren't insulated. And the wall just stayed warm and the moisture just moved through the wall. Two, we could lower the relative humidity, much like we used to do in old houses back in the 20s, 30s, 50s, whatever. We only kept houses at 15 to 20% relative humidity. We didn't add moisture to houses. That would solve your moisture problem. But in new houses where people want higher levels of relative humidity for better comfort and where we're required to put in insulation, you only have 2 choices left. One, as I showed in the animation before, make sure the wall cavity is really airtight, or 2, make sure that you have insulated sheathing. And when you have insulated sheathing, notice this, at 30% RH, if I put R5 on the outside, no chance for condensation inside that wall. That light blue line shows you no chance of condensation. Better yet, go to 1.5 R7.5, and now you can have no condensation, or at least very little condensation potential, even at 40% RH. So insulated sheathing simultaneously makes your houses more efficient, but also healthier, because I can raise levels of relative humidity to where people want them, and more durable because I have less chance of interstitial condensation. So very useful. So much so that if I put enough insulation to the outside, I can move away from things like interior poly vapor barriers and simply use painted drywall, for example. Notice that in your climate zone, I presume most of you are in climate zone 5, that if I have a 2x4 wall, as little as 1 inch of insulation means I don't necessarily need to put a defined vapor barrier other than simply painted drywall. Even on a 2x6 wall, all I need is R7.5. And notice the more insulation you put to the outside, the safer and safer the wall gets. This is out of the IRC 2012, and the fact that you showing that when you use insulated sheathing, you are helping manage vapor control risks or vapor risks, if you will. Your control there becomes that insulated sheathing. So I'll say many times over this session, simultaneously improving thermal performance by as much as 30% of when you put 1 inch of foam on, or 1 inch of insulation on the outside of a 2x6 wall, you improve from 14.33 to 19.33. You improve the wall by 30%, and you reduced its potential for condensation, which makes it safer, healthier, more durable. So pretty powerful. I just wanted to show higher levels of insulation, in this case showing the advanced framing, 20%, notice there on the left, R10 on the outside, and now we're at an effective R value of 26, over 26. In this case, we've gone from 14.33 to 26. We've improved our wall by 70%. Now, that's 2 inches of exterior insulation in this case, maybe 2.5. You're going to say, could I do more? And the answer is, of course. The next question is, so how do I install that? What does that mean for implications or applications? But now you have a sense of the performance levels that you might be looking for in your houses. So there's an interesting one as well. A 2x4 wall with R10. A 2x4 wall with R10 on the outside outperforms even a 2x6 wall with 1 inch. And this, you'll remember, matches with the new 2021 code. Remember, it said R30 or 20 plus 5 or 13 plus 10. This is why. So now you end up with a wall that's the same dimension as a 2x6 wall. Now it's a 2x4 wall with 2 inches of insulation on the outside. Didn't need to thicken up the wall, and yet I've improved its performance by 30%. Put less framing and more insulation to the outside, and I actually have a better performing wall. So those are a couple of examples of where we want to head with this. And then the question is, so how do I install this? Where does this go? Is the insulation go underneath or over top of the WRB? And the answer is it can be either. And I'll show you a couple of animations that highlights that. This is an animation provided by DuPont. This is our company has drawn this animation, but I just wanted to show you the WRB, in this case, over top of the continuous insulation. In this case, showing bumping out the window framing, buck out the window framing to whatever depth of foam that you want to use. And I keep saying foam, doesn't have to be foam, insulated sheathing that you want. And now we're going to install and offer, obviously, proper fasteners on that insulated sheathing. And just showing the fasteners, obviously long enough to get you back through to the studs and proper embedment. In this case, the WRB going over top, using again the proper fasteners to make, and proper overlaps and tape, doing the window like you normally would, a simple cutout of that window, and making sure there's no fasteners in that zone. But indeed, the proper button cap fasteners that have to be long enough, again, to get back into the, in this case, at least into the sheathing material, showing the tape joints. And now the window install is basically the same as you would normally do. That is, the only change we've made here is an extra inch, in this case, inch of insulation. But now the water resistant barrier goes in, window gets flashed exactly the same way. Some may ask, do you really need to buck out the window? Could the window actually be attached through the foam? And you would check with your window supplier. You'd say, is it okay if I nail the nailing flange through the foam back to the wood studs? But you'll ask that question. Just again, just showing proper flashing details, proper performance. I just want to highlight that it's a fairly simple change. Yes, the wall got thicker, an inch, inch and a half, 2 inches of insulation, but otherwise my procedures and processes are essentially the same. The only, not the only, one consideration is, what about the cladding attachment? So I'm going to attach my cladding through that foam. How do I do that? And you would ask your cladding supplier, and whether it's a vinyl siding, a cement board siding, a wood-based siding, or a brick, what length of fastener is it okay to use? And generally speaking, I'm just talking over the animation at this point just to move things along, but just showing the typical way of installing flashing details. I should probably rest while you guys watch this. showing that detailing of the window. So everything else is looking pretty normal, right? We're going to air seal from the inside. And as we go back to the outside, thinking about the cladding going on, so there's the finish. So now the question is, can I attach through? And you will check with your siding providers and say, what can I nail through? Is it okay? And most, in fact, all that I know of would say nailing through an inch of foam, as long as you're getting back to the sheathing or to the studs, nailing through an inch of foam is not a problem. Many will say up to 1.5 inches. I know at least one cement board supplier and one wood-based siding supplier would say they're okay with you attaching through that up to 1.5 inches. When you get to 2 inch of exterior insulation, most cladding manufacturers are saying, nah, I need you to attach to a strapping. So our next animation here is showing if indeed you are going to use more than 1.5 inches. In this case, showing R10, and then this foam, it would be 2 inch. Notice the WRB went on first. WRB went on first. Windows were flashed. So this is indeed a process change. And in this case, now the foam is the insulated sheeting's to the outside. So I need to build out some jamb extensions. Now, there are some window manufacturers that are starting to provide exterior jamb extensions or flange locations that will allow you to accommodate that extra thickness of insulated sheathing. Here, structural strapping going on with very specific screw requirements and the embedment back into the framing. And now I have a strapping that's now good for my cladding attachment. And it's important to understand in this wall that the benefit is more than just thermal. Remember, we talked about the 4 control layers: water control, air control, vapor control, and thermal. In this case, now you have a vented rain screen. That siding attachment on the cladding gives you that full 3/4 inch of vented cladding. This improves the durability of your wall, improves the durability of the entire system because I've got that vented rain screen. So yes, it's adding cost, but it's adding far more in terms of performance of the building. Incredible air tightness, incredible water management, incredible vapor control, and that really good thermal control because of that 2 inch. And there are new options coming. That is, there are people who are saying, could I do the structural layer and the insulation layer combined, right? You're seeing, I said that Timber HP, it's going to be a wood-based sheathing that presumably will do the structural. You're seeing products like Huber's Zip R, which has a laminated foam to the back of that product. So we have new entries that are trying to do more than one thing, getting you both the structural layer and the nail base and the foam all in one. So lots of new opportunities coming, and all of these can work as long as they're properly installed, properly managed in terms of their, I'll say, structural requirements, and then properly done from a water management perspective. And again, I'll mention quickly, by all means, insulated concrete forms, tremendous thermal performance. What I would say is the traditional top left R22, that's basically the same as a 2x6 wall with 1 inch of R5 insulated sheathing. And you would say, is that enough going forward? And now most of the ICF manufacturers have better options for you, or at least let's call them thicker options. So, and it's basically more foam to the outside. So I'd encourage that. Or could we be doing SIPs? And of course, and you would simply say, I want a 6, an 8, a 10-inch SIP, and that gives you a good opportunity to improve your R value. I'll show just a piece of the animation of installing those SIP panels. Still need to be made airtight, still need to think about window openings, air sealing, and so on, but just showing the SIP panels going up. This too is a process change, but a nice way to improve the thermal performance of that wall. So we're showing different options: the traditional 2x6 wall, adding insulated sheathing, or moving away from that approach and going to an entirely new wall approach, such as SIPs. And I won't play the whole thing, just in the interest of time. we'll move along. So we talked about thermal control. I just want to make sure that we touch on air control. We saw water control. That was a WRB, either inside of the insulated sheathing or to the outside. Either one is fine, depends on the type of insulated sheathing you're using. If you're using a mineral wool, then typically you're putting the WRB inside, that is putting on first. But we talked about water control. I do want to highlight air control just a little bit, and understanding the interest in that air tightness of those walls, making sure that we don't have any warm, moist air getting into wall cavities. You will recognize that we can do them from the outside, we can do them from the inside. It's been a code requirement, I always like to point out, since 2009 to make buildings airtight. This continuous, sealed, continuous air tightness of buildings. What we always like to ask is, what is the primary air barrier? Is it the drywall, the sheetrock on the inside? Is it the WRB? Indeed, could it be the foam sheathing? Foam sheathing could be the air barrier. Mineral wool, no. Wood-based sheathing, we'd have to ask Timber HP whether their product is airtight. But we have various choices here, and we simply need to decide which one is our primary air barrier. And there's not a problem with being more than one air barrier, by all means. Seal from the inside, seal the WRB on the outside, seal the foam on the outside. There's not a problem with more than one air barrier, but generally speaking, we want to identify at least one of those materials as the primary air barrier. In this case, showing an exterior air barrier, the dotted line, red dotted line, showing an exterior air barrier, and how it's helped to manage things like behind box framing and so on, if I'm all to the outside. An interior air barrier, typically drywall, some cases a polyethylene or a vapor retarder on the inside becomes your air barrier. What we often find is people using wasted efforts, putting the beads of foam or caulking. There's no need to do this extent. Even this kind of thing, using the wrong materials, foam is not a great air barrier in that location. So we find lots of cases where it's just not done correctly. There are some really good simple options. This is a gasketed system that we could be using on exterior walls. And your goal should be in that 1.5 to 2 air changes. For those of you on the passive house, you're down around 0.6 or under 0.6. So thanks for that. In existing houses, we should try to look for a 25% improvement in that performance. I will highlight there is a new technology called AeroSeal, which is I'll say blower door directed air sealing. You turn the blower door around, positively pressurize the house, put in this sealant, fog the house with the sealant. The sealant finds the holes as around this electrical box, that gray fluffy stuff you're seeing, or caulking, it looks like a caulking, is actually that AeroSeal product. And what's nice about it is it's giving you an actual report as it's air sealing. It's showing you there in the left the performance, and you can dial it up to whatever level of air tightness you want. Or we could do exterior air barriers, as I mentioned. So the WRB, for example, could be an excellent air barrier. Various materials that we can use, or the foam itself could be an air barrier. The challenge with foam, specifically as an air tightness, requires a very specific tape because the foam expands and contracts a little bit, so you have to use a proprietary tape. But we can meet our air tightness in either ways. So to finish up in terms of the speaking portion, and we'll move towards questions, we're sort of perfect on timing. I just want to highlight to you that effective R values are now the new metric. And when you start thinking about effective R values, you need to think about more cavity insulation, less wood, or more continuous insulation. And we're going to say to you, insulated sheathing is going to be normal. It's going to be one of your strategies. Why? Because it's cost effective in terms of, let's call it design. I get better bang for buck on the outside in terms of width than I do inside the cavity. I can get more done when I cover the wood, if you will. So it's really cost effective from a dimension of the building alone makes it more cost effective. And advanced framing is an opportunity, whether you choose to use it or not, but at least optimize the amount of wood that goes into the wall. Air leakage control is absolutely critical, especially the more insulation you put in the cavity, the more airtight that building needs to be, that wall structure needs to be. And understanding that no matter what you do, the drying potential of a wall gets worse. That is, when I don't have heat flowing through the wall's not able to dry as quickly. So whatever you do on thermal, you also have to up your water management details. The more insulation you use, whether it's outside cavity, exterior insulation or cavity insulation, you need to do a better job of keeping water out of your walls. So drying potential does go down. So therefore, comprehensive water management is still the biggest concern. And there are lots of great partners on this. The major insulation manufacturers, the WRB manufacturers are all really helpful in this regard to find you new systems. If you've never done insulated sheeting before, I would say all of the major companies, the Rockwools, the Owens Cornings, the DuPonts, they all have really good training programs available to you and your crews, your framing crews, in order to get that continuous insulation done correctly. So I'll just say at that point, are there questions? And Paul back up, Sarah, Egan, any questions? I may put that
Sure.
back up just as people are chatting, and Keegan, you may want the other slides up in a moment, but I'll leave that up and see if there's any questions.
Yep, there's a couple Q&A questions, but before I read them, I just want to say I've over the years have come to appreciate how important airtightness is for energy conservation, and I
Yes,
love that talking about continuous insulation. You can installing that well can help kill two birds with one stone.
absolutely.
Yeah.
Quite nice.
So we've got a couple questions. The first one is, what is the long-term effectiveness of spray foam? It says CC spray foam, continuous. I understand that might also shrink through time. Another question, are CC spray foam still petroleum-based, or is there a water-based alternative now?
So first, you're quite right. Most insulation, the fibrous insulations, the open cell, are using trapped air as their insulation. And that's why they kind of max out around, say 4.5, our value 4.5 per inch. The closed cell foams, they're the blowing agents of the foam. Those inert gases are have a higher, less thermal conductivity. You can imagine over time, inevitably, depending on where that spray foam is, those inert gases are going to leach out and they're going to be replaced with air. Okay, so the long term, and so I'm a Canadian. In Canada, we give spray foam, closed cell spray foam, a value of 6.3, the aged value of 6.3. In the US, you'll often hear 7.5. That's the short-term value is 7.5. There's no reason to believe that it gets lower than around 6 because it is very good trapped air. It doesn't physically shrink. When they say shrink, really what they're saying is the gases escape, but the pockets are then just filled with air. So we would expect the long-term value to be 6 to 6.5, still better than, higher than the standard air-based, but we have pretty good science that would say, long term, like years later, they're still at 6.5 per inch. I just saw a foam yesterday that's trying to dramatically reduce its carbon footprint. Most are petroleum based. In fact, those that aren't petroleum based, at least say they aren't. There are always two components. The one component is always oil based, and the other components now can be, you're seeing other attributes. So they're all trying to improve over time. I would say every year, reevaluate and ask them again, what's your carbon footprint now? What's your carbon footprint now? Because I'll say the sheet foam folks, the DuPonts and Owens Corning of the world, recently, within the last 3 years, dropped their carbon footprint by about 90%. They reduced their greenhouse gases on exterior foam insulation by about 90%. Now, they're still higher than a wood fiber based, but they're 90% less than they used to be. So keep looking each year to find one that makes sense. What I often get asked, Sarah, is it worth it? Ah, okay. That is the carbon that's invested in that insulated sheathing is paid for within 5 years in terms of the operational carbon that's reduced. Let me say that again. If you model the embodied carbon and the operational carbon of a wall that has insulated sheathing, whether it's mineral wool or XPS foam, the reduction in operational carbon is paid for, it pays for the embodied carbon that went into it in less than 5 years. And so it's still a very worthwhile thing. Would you like it to be lower? Yes, you'd like it to be lower than that, but it's still a really good return on carbon invested in climate zone 5. Hopefully that answers.
Great, thank you. Someone is mentioning there's also now an exterior rated hemp-based panel from Hempitecture.
There you go. And thank you for those. We're starting to see new materials. That's wonderful. We do need to recognize, okay, what are the water management details for that? Not that they can't work, but you'd have to think about where's my WRB going? How am I managing that? Where am I putting the windows in those structures? Because I presume they would not want them to see bulk water. So WRB is going to the outside. The thicker I am, and W rated to the outside. Now I got to flash it back to the windows. Where are the window placements? So I like all of those choices. Just be careful of your water management details.
Good. Is insulated sheathing better with sheathing on the cold or warmer side?
We often get that. Could I do it on the inside? And the answer is, from a thermal perspective, yes, you can do it on the inside. So in a retrofit, could you line a wall? You've stripped off the old plaster and line it with an inch of and so on? Sure. What you'll find is it's tougher to apply on the inside because there's more intersections, and you often don't get behind the intersecting walls and so on. So there's maybe you don't necessarily get all of the thermal bridging. You don't reduce all the thermal bridging. So on the wall itself, fine. But what about at the rim joist? What about the window trims? What about wall intersections? Am I getting full value on the inside? Second, we like it on the outside because it keeps the wood warmer. In wood-based structures, warm equals dry. So with the insulated sheathing to the outside, it's keeping the structure of your building warmer, and therefore it has a benefit from a durability perspective. So you have a thermal consideration and you have a durability perspective. So we prefer it on the outside. Well, you're on mute, sir.
Thank you. There has been some discussion that the code minimum continuous insulation levels are still potentially risky for condensation within the wall. Do you have any thoughts on this?
Yes, and thank you for bringing that up. Think about this. There's already a risk with OSB. If you stick your finger in a wall, I don't know how cold you are there today, but I am at about 20 Fahrenheit. If I stick my finger in a wall, there's condensation there, there's moisture there. With OSB, the OSB kind of absorbs some of that moisture, so it has to be wet for a fairly long time before we have an issue. Understand that when you put insulated sheathing on the outside of that, a foam-based impermeable, that's actually making the wall better because it made the OSB warmer, so less chance of condensation. There will still may be condensation at 1 inch at R5, but there's going to be less than there is now. So it's actually a good thing. The more you add, the first inch you add makes the wall better. Doesn't make it perfect, but it makes it better. If you want no condensation in the wall at all, well, now you're at 7.5 to 10. But putting 1 inch on R5 is better than no inches.
Next one is using a single top plate a code violation?
It's a good question. And I would say it depends. What's your structure? Are the studs lined
Sure.
up or are the floor joists lined up? So that's why most don't get the single top plate, but it's entirely possible to do. You just have to have stacked framing and show the structure of the floor above, and then you're in good shape. Um, but most don't actually do it for that reason. Well, it's also the height, right? All our drywall is all set up for specific heights. Our studs are all set up for specific heights. But that APA guide at apa.org will show you how to do single top plates in every climate zone if you wanted to.
Are rain screen cavities sufficient with air opening only at the bottom of the cavity?
Well, there's two things. Thank you for that. You'd like it to be vented, which means top and bottom. Like you want air movement. You actually want the convective loop behind it. That said, if and some would say, well, then that's going to vent up into the soffits. No. You create a freeze board detail that vents it out, not going into the soffit. I don't want it venting into the soffit or into the attic through the soffit. So you can put a detail that allows the vent to come out. That said, the airspace itself, even without venting, is valuable because it drains water much better. And airspace drains water much better. So it would seem a shame to do a rain screen without venting top and bottom. But even if you didn't, that wall is still better because it got really efficient drainage. It doesn't have the air movement, but it has efficient drainage.
Thank you. There's two roof questions from different people. One is
Is that
what
next
type
Friday, Keegan? Is that next Friday?
what type of continuous insulation do you recommend for roofs? And is there a good way to continuous insulation for pitched roofs?
Again, I love this question. Joe Stieber designed, I don't know if folks probably know Joe Stieber, buildingscience.com. He's got some really good details for how to get rid of ice damming and specifically in high snow load areas. And he shows insulation on the top. In fact, he likes to say it this way: take your wall and do this. So if you have 2 inches of the wall, 2 inches on the ceiling, and the more you put in the cavity in that ceiling, the more you want on top, right? You always want to maintain that ratio. And it really just gets down to what's your appetite or budget for screws. Because I put 4 inches on my roof and the screws themselves, because now we're talking 4 inches of foam and strapping. And that was 8-inch long screws, roofing screws. And it was something on a relatively modest house, $3,000 worth of screws alone. In fact, in some respects, the fasteners cost more than any other individual part.
I
So
think we should all be investing in long fasteners.
long fasteners, and in that case, the same rules apply. Mineral wool can be used there. XPS can be used there. Traditionally, it was in flat roofs. It was polyiso foams that are used in flat roofs, partly because of the extra R value and their moisture resilience. But on a pitched roof, cathedral, if you will, you have your choice of materials. It's not a problem. Again, where's the WRB going? Where's the water management layer going? Still really good air tightness, but huge value especially in high snow load areas to put insulation on the top. And 2 inch is a good start. Anything under 2 inch, to my mind, is a little bit of a waste of time on a roof. But that over roofing is a really good idea.
Great. I think we've got two more left. Um, this is actually a question about your prior webinar. It says,
Yeah.
in your previous presentation, you had a picture of your house, question mark, with BIPV roof shingles. Given your
Yes.
personal preference, how does it perform compared to standard install? And what brand were the roof shingles?
I don't mind giving you a brand because it's no longer made. It was actually made by Dow. It's
Oh
called
no.
Dow Powerhouse.
Sorry, can you say that again? Dow.
It was Dow Powerhouse.
Okay, thank you.
They sold that division off to a company called, I think it was RGS out of Denver. And I don't think they're still making them. I've seen in pictures Tesla. I've never seen Tesla on a roof. GAF now has a shingle. There's a few others out there. I would say I did it not for the performance of it. I did it for the uh, to try it and the aesthetics, because people would say to me, architects would say to me, I don't like the look of solar panels. And so I wanted to show what was possible. Its performance, they've been on there 10 years now. The performance is still very close to, I haven't seen any change in performance as of yet. They look great. They're integrated into the roof, no problems with it at all. So I like them. I would still say they're not as cost effective as panels, and they're not as efficient as panels. But if the aesthetic is of concern and you're paying for the aesthetic, go for it. There's now, like, GAF has a really, in fact, two versions or two series of product that both of them look really good to me aesthetically.
Great, thank you. And this looks like the last one. So if anybody has some questions, get them in fast. I see some folks putting a second layer of sheathing above the furring strips on the roof for moisture control. Is that necessary, or can you rely on just the roofing material, assuming standing seam metal?
Yeah, exactly. I'm going to defer that one because we weren't talking roofs today. Again, I would say go to buildingscience.com, or Owens Corning has a really good guide for roofs on exactly that insulation. In my case, did sheathing and a water and then a shingle underlay. Mine was a shingled roof. So it depends. I would say I would be talking to the roofing company and your structural engineer to say, do I need this or not? It's hard for me. There's just too many conditions, situations that it's difficult for me to give a one solution answer there. Well, thank you all for the
All
questions.
right.
Thanks for narrating.
Yep.
Appreciate that. Keegan, I put up the slides again. Is there any one particular one that you think would be appropriate to leave up as we say goodbye?
No, this is great, Gord. Thank you so much. Yeah, really appreciate the last two sessions you were able to join us for. Sarah, thanks for moderating and representing Build Green Connecticut. I'll just plug that we're currently working to put together programming for 2026 for this training initiative. We'd love to hear from you all if there are suggestions, topics, subject matter experts that you want to hear from. Let us know. Passive House Training CT at ICF.com, or if there are folks that should be receiving the invitations to these trainings that are currently not, have them email us to sign up and get on that distribution list. But otherwise, yeah, thanks to everyone for joining today. Gord, really, really appreciate you joining and sharing your expertise. It's always a pleasure to have you. And Sarah, thanks again, and we'll see everyone soon. Happy holidays.
Thanks again, Keegan, for the opportunity. Happy
Bye.
holidays.
Appreciate it.
Thank you
See
all.
everyone soon. Thanks.